We'll start today's session. So I hope you have gone through the lectures and we'll solve some of the problems and mostly they will clarify your doubts. And if you have any doubts, you can also ask. Okay. So last time I think Perumala Swami asked the question that suppose you know that the 3 by 4 matrix A has the only vector S which is 2 3 1 0 as the basis for the null space. The rank of A is okay. So let's see what it is. So the rank of the matrix. So rank of the matrix is nothing but the number of independent rows or columns, and we'll say this is equal to R. So this A matrix is let's say M by N, where M is equal to 3 and N is equal to 4, and the null space that we are interested in Ax is equal to 0, where X belongs to null space of A. So that is the meaning of null space. So if we take the product of A and X, it will be 0. So the dimension of X, if you see, so if we have the A matrix which is M by N, so X will be there are n columns, so n cross 1, so it is like A is equal to, in this case it is 3 by 4, so there are 3 rows and 4 columns, and if we see the X vector, so let's say Ax is equal to, so this matrix is A and this is X. X will have component x1, x2, x3 and x4. So ideally, if x1, x2 and x3 and x4, these are the 4 components, so X should span the 4 dimension, but X doesn't have all the variables free. So if you see that the number of columns, okay, so there are depending upon the number of free variables, the dimension that is spanned by X will get decided. Okay, so what is the number of free variables? Here number of free variables is equal to, so here you can see that it is M cross N, so there are n columns, so n minus rank will be the number of free variables, and that is nothing but the dimension of null space of A. Or you can see this is the number of free variables, and if we take the X, if we see the X can be let's say V1 is the first component time C1, and so C1 is, let's say, first free variable, and C2 is another free variables and times V2. So as many free variables will be there, that many that will be the dimension of the null space. Okay, so if we go back to the question, so X is, so the null space is spanned by only one vector, so we can see that so the dimension of null space of A, which is nothing but number of columns minus rank, which is 1. So this is only one vector can span this null space, so it means it is one dimensional space, and the number of columns are 4 and minus rank, So we can see that rank is 4 minus 1, which is 3. So that is the answer. I think this is clear now. Okay. Is there any doubt? Okay. Okay, I think it is clear. Yes, sir. Means I. Okay. I think the doubt is clear. Okay. So we'll go to the next question if it is clear. Okay. So the next question is, find the solution y at x is equal to 2 of the differential equation x square y prime plus 2x y plus x plus 1 is equal to 0, and the boundary condition is given. Okay, so what we'll do is, first we'll write this equation in the our regular form, and then we'll try to solve this. Okay, so so the thing that is given is the initial state, or the solution, the like at x equal to 1 the value of y is given, so we can determine the y value at x equal to 2, and we can see that it is first order differential equation, so one condition is enough to solve it. So the question is, x square y prime plus 2xy minus x plus 1 is equal to 0. Okay, so x square y prime plus 2xy is equal to x minus 1, and we can directly see that this, and this is the, if you see this x square as u, then 2x is the derivative of that. So let's say if we write let's say this m, and m is equal to this, and this is m, and this then, so dou m by, actually this is not the correct, we'll just directly by observation we'll go with this, because anyway it will turn out to be okay. So if we see this x, and this is the derivative of that, so we can just write x square y prime, and this is dx square by dx and y, and x minus y. So we can see that this is the nothing but the x square y dx and x minus 1. So this is the form we have, and then the the left hand side was total derivative, so we don't have to do anything here. And if we solve this, okay, so what we get is x square y is equal to x square minus x plus c. I think it's correct. Okay, so x square y is equal to x square by 2 minus x plus c, and we can write y equal to so y equal to 1 upon 2 minus half plus c by x square, and y at x is equal to 1 is given, which is 0. So if we see y at x is equal to 1 is 0, and we are interested in y at x is equal to 2. Okay, so the only thing that we are supposed to determine is c. So if we substitute x is equal to 1 in this equation, we'll get y equal to half. Oh, this is half minus half plus c, and y is equal to 0. So if we see that c is equal to 0, and then if we substitute this into this equation, we'll get y is equal to half minus 1 upon 2x, and if we substitute x is equal to 2, so y at x is equal to 2 will be half minus 1 by 2 into 2, which is half minus 4, which is 1 by 4, which is 0.25. okay, so we can see that the 0.25 is the correct answer. I think this is clear. Okay, so we'll go to the next question. So the determinant of the matrix is given, and we are supposed to find the determinant. So 5 1 3, 5 1 3, and 0 2 1, and 2 9 3. Okay, so the determinant of A is nothing but 3 0 2 1 2 9 3. Okay, so we can directly, instead of starting with the regular first row, we can just start with the second row, because we can see that there is a 0 at the first place. So the 0 we will not consider. Then we'll go into 2, and then 2 into, then we have to consider these elements, 5 3 2 3, and then we will go with 1, because it is at 2, so the position is 2 comma 3. So we can see that summation is odd, so we have to go with minus sign, and as there is 1 present, so minus 1 times 5 1 2 9. Okay, so the answer will be 15 minus 6 minus 1, 45 minus 2. Okay, so 2 into 9 minus 43. Okay, so 18 minus 43, which is minus 25. Okay, so the determinant is minus 25. And also you can try doing the row operations, and the determinant will not change, so that also you can try. Just interchange the do the row operations, and try to make more zeros possible into this matrix, and then see if that can simplify. Yep, that you can try. So D is the correct answer, which is minus 25. Okay, because this is 3 by 3, so might be easy to do directly, but when it's larger matrix, I think you can do the row operations first, bring more zeros into the matrix, and try to find the determinant after that. Okay, so we'll go to the next problem. The bismuth 210 has a half-life of 5 days. If there are initially 600 milligrams of bismuth, how much is left after 6 days? Okay, so what is given is the half-life is 5 days, and what we want to find the bismuth which is present after 6 days, and if the initial quantity is 600 milligrams. So we'll just write the law for this integration, which is the mass at the active radioactive element, the rate at which it decays will be proportional to the mass that is present at this instant, and it will be negative. So in order to make this quantity negative, we are giving the minus sign here. Okay, so if we integrate this, we can use the variable separable form, and then it will be this way. And then on integrating, let's say m0 to m and t equal to 0 to t, so we'll get log of m by m0 is equal to minus lambda t, and m is equal to m0 e raised to minus lambda t. Okay, so this is the equation that gives how much, if we have m0 which is the initial quantity available, and after t time how much mass will be left. So this is the mass will be the function of time. Okay, so we can use this equation here directly, which which relates the both mass, or we can use this also, which is not much difference. So what is given is a half-life is 5 days. So if we have m which is nothing but half of the m0 at t equal to 5 days. Okay, so this is given. So if we substitute this into, let's say we'll use this equation, so what we'll get is half m0 equal to m0 e raised to minus lambda, and t is 5 days. So half is equal to e raised to minus lambda into 5, and taking the log on both sides, natural log and minus sign is absorbed inside 5 will give the lambda. Okay, so this is the value of the lambda, and we can compute, or we can just keep it this whatever we have. So we will find out after 6 days how much quantity will be there. Okay, so m equal to m0 e raised to minus lambda t. So m we want to find out, and initially it was 600 milligram, and e raised to minus lambda, we know lambda is log 2 by 5. Okay, so we can compute and then substitute log 2 by 5 value directly here, and then time is 6, and if we do the whole computation, okay, so that will be 261 milligram. Okay, yeah, so this is the correct answer. Okay, I hope this is clear. Okay, so the next problem is we have to solve the ODE, and it doesn't seems to be in the direct, like the conventional form. We can see that this is the ODE where there is a second derivative x square is present, and where is the first derivative x is present, and then this is no derivative, so x raised to 0 we can say present. So how to solve this type of equation, we'll see. So x square y double prime plus minus x y prime plus minus 3y is equal to 4x. Okay. So what we can do is we can start with x is equal to e raised to z, and so we'll see how it will simplify the solution. So if we use x equal to e raised to z, we can let's say we will take the dy by dx. So this y double prime here is nothing but dy by dx. Okay, so what we are doing is we are changing the variable. So if we'll use the chain rule to simplify this, and then if you see this, z is equal to log of x. So dy by uh, okay, so this is our substitution that we are using, and then we are finding out the what will be the dy by dx if we use that. So if we use this dy by dz, and dz by dx will be 1 upon x. So you can see that if we use this substitution, this x will get cancelled with this x, and things will get simplified. Okay. Now we can what we can do is we also need double derivative of y. So we'll do the second derivative square, and then we'll use the chain rule, dx dy by dx, and so okay, I will just skip this. Okay, so what we are up to is this already we have. So what we can do is dz dy by dx, and dz by dx. Okay, so dz by dx is already 1 upon x, so that we can write directly, and now we will differentiate the dy by dx with respect to dz. So what we'll get is d square y by dz square 1 upon x, and minus because 1 upon x is there, so dy by dz, and yeah, so it is minus x square, and dx by dz, dx by dz will be dx by dz will be e raised to z, which is nothing but x again. So it will be, I will just write dx by dz here. Okay, so dx by dz is nothing but x. So finally what we will get is the double derivative of y with respect to x will be 1 upon x in bracket the second derivative of y with respect to z, the second derivative of y with respect to z, sorry, x. Okay, and so I will just use this x and cancel it with this x, so 1x only will remain here. So minus 1 upon x dy by dz. Okay, so if we take out this x square out, so we'll get x square, and then d square y by dz square minus dy by dz. So now you can clearly see that if we use this substitution, wherever we have double derivative with respect to x, we are getting x square out, 1 upon x square outside, and where we have first derivative, we are getting the 1 upon x outside. So that can get cancelled with this x, and where the double derivative is x square will get cancelled, so we'll get the our regular form for the linear differential equation. So what we'll do is we'll substitute these values. So x square, and let's say x square is outside, and so we'll substitute into this equation. So x square is outside, and then we'll substitute y double prime, which is this is the first term, and the second term is minus x into y prime. So the y prime, we have the expression which is 1 upon x. So this is the expression dy by dz. Okay, and the last term is minus 3y, and is equal to 4x. So 4 instead of x, now we are what we will write is x, instead of x we will write e raised to z, e raised to z. Okay, so x will get cancelled, and we'll get d square y by dz square minus dy by dz minus dy by dz minus 3y equal to 4 e raised to z, and this 2 will get add up. So d square y by dx square minus 2 dy by dx, oh sorry, it is there is no x, now we are in z. Minus dy by dz, oh sorry, minus 3y. Is equal to 4 e raised to z. Okay, so we can see that now it is pretty straightforward, at least the form looks simple. So we'll use the notation where d by dz will denote by d, and solve this. So d square minus 2d minus 3 and y, or you can say that y equal to e raised to dz. So that is also fine. Anyway, whatever this notation or this one is fine. Is equal to 4 e raised to z. So so we'll find out the y. So y particular. Okay, sorry, we'll find the complementary form first. So in order to find the yc, what we are supposed to do is equate this term to 0, which is similar to find the null space solution. And so first we'll determine what d values that will lead to this. So you can see that d minus 3 and d plus 1 y is equal to 0. So we can write the solution, which is, so these are the roots, and if these are the root, we can write y is equal to c1 e raised to 3z plus c2 e raised to minus z, and z is z, so x is equal to e raised to z. So you can see that this we can write c1 x cube plus c2 x raised to minus 1. So this is y complementary solution. Okay, so now we have the complementary solution. So what we'll do is we'll find out the particular solution. So particular solution, in order to get, we'll use this equation where we have d square minus 2d minus 3, and we have to use this term which is on the right side, 4 e raised to z. So I will use the direct method where we can see the coefficient of this. Let's say if we just go back, or let's say I'll add this right now. Okay, so so let me explain. So we have, let's say, y equal to e raised to ax. So if we apply the d to the y, which is nothing but dy by dx, what we'll get is a e raised to ax, and if we apply n times, so it is nothing but d square y by dx n time, it will be a raised to n e raised to ax. So we can see that if we have some polynomial form for this phi d, which is nothing but a n dn plus n minus 1 dn minus 1, so on. And let's say we apply it to the, so phi of d e raised to ax is nothing but what we'll get is an, and where there is n derivative, we'll get a raised to n plus a n minus 1. So a are here coefficient, but just don't mix with this. A raised to n minus 1, and so on, and finally e raised to ax. So we can see that it is nothing but phi of a e raised to ax. So if we say that if we apply this the 1 upon phi of d on both sides, so we'll so what we will get is e raised to ax phi of a 1 upon phi of d e raised to ax, and that is nothing but 1 upon phi of d e raised to ax is equal to 1 upon phi of a e raised to ax. So we'll use this identity directly in this equation, where what we are doing is in this, whatever is there on the denominator, we are substituting, instead of d we are substituting the coefficient which is present in here, e raised to ax. So we can see that the coefficient is 1, so we can directly substitute that here, which is 1 square minus 2 into 1 minus 3, 4 e raised to z, and that will give 1 minus 1, 1 minus 2 minus 3, which is minus 4, so it is minus e raised to z, and sorry, so minus e raised to z is nothing but minus x. So we have this y particular solution. Okay, so what we'll do is we'll combine both and write together. So y is nothing but y particular plus y complement. So y particular we just got to be equal to x minus x, and y complementary is c1 x cube minus c2 x raised to minus 1. Okay, so this is the solution for the equations. We'll see which matches with this. Yeah. So this D matches with the answer c1x cube plus c2x raised to minus 1, c2x raised to minus 1 minus x. Okay, so this is the correct answer. Any doubt in this? Okay, I hope this is clear then. So we'll go to the next question. Okay, so the next question is the general solution of the ODE y double prime minus double derivative of y minus 4y is equal to 8 e raised to 2x each. Okay, so we can see that this is somewhat similar to what we just derived, but I will just write one exceptional case, and then we'll see what to do with this. So what we have is y double prime minus 4y is equal to 8 e raised to 2x. Okay, so what we will, so the y solution will be y particular solution plus y complementary. So we'll start with the complementary solution first. So y complementary, how we will get is y, let's say complementary plus, so minus 4yc is equal to 0. So we'll again use the notation which is denotation, which is easier. So secant minus 4 d square, and yc is equal to 0. So we can find the roots for this. So the roots will be d minus 2 and d plus 2 yc, which is equal to 0, and we can write the complementary solution with these roots, which is c1 e raised to 2x plus c2 e raised to, and this is minus 2x. Okay, so this is the complementary solution, and what we'll do next is find the particular solution. So y particular we will get by getting this d, let's say this phi, or one second. Okay, so what we will do is we'll just write this itself as here y equal to 8 e raised to 2x, and then this will say, which is, let's say, phi of d, y is equal to 8 e raised to 2x. So we will, like, on both sides we'll operate the 1 upon phi, 1 by phi of d. So what we'll get is 8 e raised to 2x. Okay, so what we can do is we can just substitute this coefficient 2 into this polynomial, but the problem here is 8, let's say, so we have the 2 solution, which is plus 2 and minus 2. So if we directly substitute this, the one of the term is going to be 0. So what we will do is we'll just keep one term as of now as it is, and we'll substitute this 2 into the one of the term. So we'll operate by this term first, and what we'll get is 1 upon 4 e raised to 2x. Okay, so 2 1 upon d minus 2 and e raised to 2x. Now this is the problems. I'll just explain this one. So in general, if we have this d minus m, any f of x, it is nothing but e raised to mx integration e raised to minus mx f of x dx. Okay, so we'll use the same equation here and try to solve this. So what we have is 2 1 upon d minus 2 e raised to 2x. So 2 into 2 into e raised to 2x integration e raised to minus 2x into f of x is e raised to 2x dx. Okay, so 2 into e raised to 2x, and this will get cancelled, and then it will integrate to x. So this is nothing but our particular solution. Okay, so if we are wondering how this form is there, so I will just explain why we should use this form, or like this is the basic equation. So if we have dy by dx minus my is equal to f of x, and that is nothing but same form as this one, but it is direct form. So what we can see here is if we multiply this whole equation, let's say by u, so u into, or you know about integrating factor, you can find out that integrating factor for this whole equation is e raised to minus mx, and that is nothing but based on just this minus m we can find out. So you can check out that. So what is the integrating factor for this equation, that you can try as an exercise. But if we, let's say, multiply this whole equation by e raised to minus mx, it will be m e raised to minus mx y into f of e raised to minus mx into f of y. So now you can see that this term is the total derivative, which is e raised to minus derivative of this term, and the right side is minus mx f of y. Okay, so now we can okay, I'll add new slide. Okay, so what we have is d e raised to minus mx y dx is equal to e raised to minus mx f of x, and if we integrate both sides, what we'll get, e raised to minus mx f of x dx, and on the left side we'll get e raised to minus mx y. So y is equal to e raised to mx e raised to minus mx f of x dx. So that's how this form has come. And if you go back and see this equation, so what we have is d minus m y f of x, and we have y equal to 1 upon d minus m f of x. So you can see that this whole thing is nothing but and d minus m f of x. Okay, so this is the form which is the basic equation for the like whatever shortcut methods that has been developed. So this is the like important form. You can just practice with that, and then there are methods which can be used directly, such that whatever we are using here, where we can directly substitute this uh, 2 into this method, and all this has come from the same equation. Okay, so coming back to the whatever solution we have got, so y is equal to yc plus yp, and we'll go back and see what we have got. So y particular we have found out to be 2 e raised to 2x into x, okay, and y complementary is c1 e raised to 2x and c2 e raised to minus 2x. Okay, so this is the total solution. Okay, so okay okay, so we have this c1 e raised to 2x, c2 e raised to minus 2x, and 2x e raised to 2x. This is the correct solution. Okay, I hope this is clear. Any doubt in this? Okay, so we'll go to the next question. So if matrix A is 5 by 3, B is 3 by 5, and C is 5 by 1, and D is 5 cross 3, all the entries are 1, which of the matrix operation is valid? So okay, so we'll test first of all the operations. So A is 5 by 3, B is 3 by 5, C is 5 by 1, and D is 3 5 cross 3. So if we take the ABD, so you can see that A is 5 cross 3, B is 3 cross 5, and D is 5 cross 3. So you can see this matches. So this number of columns matches with the number of rows, and here also the number of columns matches with the number of rows. So this is a valid operation. Okay, so now so this is correct. Then if we go to the next option, which is A into B plus C, so B is 3 by 5, and C is 5 cross 1, so which is not valid operation, addition for the matrix. They both should have the same number of rows and columns, so this is not valid. And DBA, if we see DBA, so D is 5 cross 3, B is 3 cross 5, and A is 5 cross 3. You can see that this also matches the number of rows and columns, so this is also valid operation. So these two are the valid operation. Okay, okay, so I hope this is clear. So we'll go to the next question. The next problem is the solution of the ODE. So ODE is given, and with y0, and the first derivative is given. Okay, so we'll start solving it. So set d square by dx square y plus 2 dy by dt plus y is equal to 0. Okay, and then the conditions has been given. So first of all, so you can see that this right hand side is 0, so it is homogeneous, and then we don't need to find the particular solution will be 0, so only complementary solution we are interested in. So d square, okay, so we'll use this d notation, plus 2d plus 1 y is equal to 0, and you can see that d plus 2 square is equal to 0. Okay, okay, so now you can see that there is a repeated roots, so d is equal to 2 and 2 once again. So in this case, the solution will be of this form. So let's say this is m, so this both roots are m, so it is c1 plus c2x e raised to mx. So this actually you can derive using the basic equation that we just saw. So this you can try, where first of all I will just explain the steps, you can try out as exercise. So okay, oh sorry, this is actually the roots are 1. Okay, so here you can start with d plus 1 and d plus 1, and let's say this is y and is equal to 0. So you can consider this whole term as z, and it's 0, and now you can use that equation to solve for z, and once you have the solution, then put back, like use this expression for z and then solve it again. So yeah, you can try it out. Okay, so this is the solution if there are repeated roots. If these roots are different, m1 and m2, then the solution would have been c1 e raised to m1x plus c2 e raised to m2x. Okay, but the roots are minus 1. Okay, so we will substitute that here. So y is equal to c1 plus c2x e raised to minus x. Okay, so this is the solution, and if we substitute the initial conditions that has been given, so y is equal to c1 plus c2x e raised to minus x. Okay, so what conditions are given? Y, so both y and y prime are 1 at x equal to 0. So y is equal to 1 and y prime at x is equal to 0 is also 1. So we'll substitute y at 0 is equal to 1. Let's say we'll say this equation 1 in equation 1. So what we'll get is 1 is equal to c1 plus 0 and then e raised to 0, and we'll get directly c1 is equal to 1. Now we will take the derivative of 1. So differentiating 1 with respect to x, what we'll get is y prime is equal to c1 plus c2x and let's say minus e raised to x plus then we'll differentiate these terms in the bracket, which will be c2 e raised to minus x, and at x is equal to 0, we'll get 1 is equal to y prime is 1, so we just substituted 1 and then minus, so c1 is 1, 1 plus x is 0, and e raised to minus 0, which will be again 1 plus c2. Okay, so what we will get is c2 is equal to 1 minus, this will be minus 1 and it will go on that side, so 2, so c2 will be 2. So we have c1 is equal to 1 and c2 is equal to 2. So y is equal to c1 is 1 plus 2x e raised to minus x. Okay, so instead of x they have used t, so we can replace that and see. So we got 1 plus 2t and e raised to minus t. Okay, so instead of x we will switch to t, so y is equal to 1 plus 2t e raised to minus t. Okay, 1 plus 2t e raised to minus t, 1 plus 2t e raised to minus t, so this is the correct option. Okay, I hope this is clear. So in this equation there was no particular solution. Yeah. Okay, so the next question is, which one of the following is linear non-homogeneous differential equation, and x and y are respectively independent and dependent variables. So we can start here. So you can see that the right side is 0, so it means they are homogeneous, and in question they have asked non-homogeneous, so either this is the candidate or this is the candidate. Okay, and see in equation C you can see that this y is the dependent variable, and it is like the y is present in the exponent, which is non-linear, so this is not the correct answer. So the only option that is left with the A, and you can see that this is the dependent variable, which is y, it is has the power which is only 1, and x, even the x is in the exponent, but that is actually independent variable, so that is fine. So the A is the correct option. Okay, so we'll go to the I hope this is clear. Okay, so the next question is, if the characteristic equation of the differential equation has two equal roots, then the value of the alpha are. Okay, so here we can say, let's say y equal to e raised to lambda x. So if we use that we'll get lambda square e raised to, we'll substitute that into this equation, and what we'll get is e raised to lambda x plus 2 alpha lambda e raised to lambda x plus e raised to lambda x is equal to 0, and this all terms will get cancelled. We can put it on the right hand side, and lambda square 2 alpha lambda plus 1 is equal to 0, and this is nothing but similar to the d form. So instead of lambda we would have directly substituted where is the second derivative, we can go with d, so it doesn't matter. Okay, so if we find the roots for this, so what we'll get is lambda is equal to minus 2 alpha plus minus So this is quadratic equation. We can find the roots, and it will be 4 alpha square minus 4ac 4 and so a is nothing but 1 and c is 1, so it will be 4 divided by 2a, so which is 2. Okay, so we'll get this form alpha square minus 1. So in order to, so if we can see that this lambda 1 and 2, so if lambda 1 corresponds to the addition, the second will corresponds to the subtraction. So if we want both roots to be equal, so this term has to be 0. So we will write alpha square minus 1 is equal to 0, and that's how alpha will be plus minus 7. So for the unique roots, alpha should be plus or minus 1. So this is the correct answer. Okay, I hope this is clear. Okay, so that's all questions I had for today. But I will take one more question after this, and then we will close the session. Okay, so right now we saw uh, that if we have the differential equation which might be of this form, so the first step that we followed is y equal to y complementary plus y particular solution. But this particular solution we have to use the equation on the right hand side, and to get the particular solution. So if we see how we solve this, is yc is equal to 0. So that is the first we will solve, and the second we will solve yp, which is f of x. So this is so this is the two steps procedure we have followed. But you might have come across the within the lecture that there is another method which can be used to find the yp. So let's say we have the complementary solution available. So let's say this is phi of d is second order. So if it is the second order, so what we will get is y complementary, which is c1, let's say y1 plus c2 y2. Okay, so we'll solve one problem, but we'll see how this is how this like the method based on Wronskian, how it is like how it came and how it can be applied. So yc is equal to c1 y1 plus c2 y2. So in order to find the particular solution, what is done is, so here c1 and c2 are constant. So instead of that, they are treated as like a variables. We will use other. So let's say u times y1 and v times y2. So when the f of x has some complicated form, so in that case we can directly use yp to be u y1 and v y2, and solve this. So here this both will be the function of x, and instead of being constant. Okay, so let's say we have the okay, so what we have started with is the phi of d is second order. So let's say phi of d is a d square plus bd plus c. So this is the form we are looking for how to solve, and then right hand side can be any function. So let's say, so this is the particular form, and then we are saying that we have already solved this first equation, and then we are interested in the particular solution now. So phi d of yp is equal to f of x. Okay, and so that's one we want to solve, and what we have started with is yp is equal to uy1 plus vy2. Okay, so what we can do is we can take the first derivative of this. So y prime of p equal to u prime y1 plus, let's say, v prime y2, and then we will take the derivative u y1 prime plus v y2 prime. Okay, so what we will do is uh, we are having this term where u and v are unknown. So instead of dealing with the derivative of u and v, what we'll do is we'll substitute this to be equal to 0. U prime y1 plus v prime y2 equal to 0. So this is just for simplification, or you can say this is some orthogonality property between the vector. But as of now you can just say that u and v are unknown, so in order to simplify this we are substituting that equal to 0. So this is the one equation that we have, and we will go to now the second derivative, because this is nothing but d into yp. Okay, so if you see this the equation that we are interested in, it have the double derivative, and so what we have is yp prime is equal to u y1 prime plus v y2 prime. Now if we take the derivative of this yp prime, we have to differentiate u y1 prime plus v y2 prime, and if you differentiate, what we'll get is u y1 double prime v y2 double prime plus u prime y1 prime plus v prime y2 prime. Okay, so what we'll do is we have now this is equivalent to double derivative of yp. So what we'll do is we'll substitute this all, this one, and this one, which is nothing but d of yp. Okay, so we'll say this is let's say 1, and this is 2, and we will substitute into this star. Let's say, so we'll substitute 1 and 2 into star. So if we substitute that, what we will get is a into d square yp plus b into d yp plus c into yp is equal to f of x. And if we substitute this, what we'll get is u y1 double prime plus v y2 double prime plus a u prime y1 prime plus a v prime y2 prime, and the second term is we'll write b into this one, b into u y1 prime plus b into v y1 prime, and let's say the last term c into y, so plus c into y1 plus c into y2. Okay, okay, so u and v will come here because this is the one term and this is another term in this yp. So what we have done is we have used this three equations, and then we have substituted the first derivative of yp and the second derivative of yp into this equation. Okay, so you can practice it once again, but I will just show you what is happening here. So you can see that this three terms have u in common and these three terms have v in common, and just right side f of x. So if we take the u common from this, you can see that a y1 double prime plus b y1 prime plus c y1 and v forgetting a y2 double prime plus b y1 prime plus cy2 plus a u prime y1 prime plus a into v prime y2 prime is equal to f of x. Okay, so now you can see that this is nothing but the actual differential equation that we are trying to find out, and then we have already see that this complementary solution, which is c1 y1 plus c2 y2, and this phi of complementary is already 0. So if we see these two terms, so they are ideally 0. Okay, so what the equation that we are left with is this equation. Okay, so we have a u prime y prime, this y1 prime, a v prime y2 prime is equal to f of x. So this is one equation, and next equation that we we have imposed this condition y prime u1, y prime okay, u y1 prime plus v y2 prime is equal to 0. Okay, oh sorry, so this is not, this is the equation that we have imposed. There is no derivative here in y, but we have derivative in terms of u and v. Okay, so you can see that we have two equations, and what we are interested is in determining the u and v. So this is nothing but if we are having the equation ax plus by equal to c, and c dx plus ey equal to f. So we can use the Cramer's rule to find out x, y. So similarly we can find out u prime and y prime here. So u prime will be, so u prime, you can see u prime is so wherever u is, we'll write this f, and then it will be y2 and a y2 prime, and in the denominator will be y1 y2 a y1 prime a y2 prime. Okay, so So we can write it 0, okay, f and y2 a. Okay, so what we'll get is 0 and y2 f, and in the denominator we'll get this term where we'll take a as a common. I think a should have gone. Okay, so y1 y2 and y1 prime y2 prime, and so this is known as the Wronskian. So you can see how this Wronskian has come into the picture. Okay, so I think I did some might have done some mistake, but okay, so I think you can see that this is how the Wronskian comes into the picture. So I will write the final form for this. I think this a should not come here, so u is equal to integral minus u to f of x dx, and denominator will be y1 y2 y1 prime and y2 prime. Okay, so this one, or you can say that this a has come because we considered it fairly general, so it was like a was here, but if we start with the form where a itself is 1, so in that case if a is equal to 1, and that we can always do by just dividing everything by a. Okay, so that doesn't matter. So if we just say a is equal to 1, so this everything will be fine. Okay, so if a equal to 1, so this will be the equation. So I think whatever we did is correct, but only the case is if a equal to 1, this what we will get. And similarly what we can do is determine the v prime, and similarly you can do. So I will just write the equation for v. Okay, so v will be integral of y1 f of x dx, and divided by y1 prime y2 prime. Okay, so this is how the u and v can be determined, and that's how this Wronskian also comes into picture. And this comes because we have imposed one of the condition here. This is one condition we have imposed here, which is tells that if we take the differentiation, so what we have done is we have started with particular solution, which is the combination like which has been formed by the using the particular not particular by using the complementary solution. This is y1 and y2, they corresponds to the complementary solution, but we use the u and v, which are now the function of x. And then when we take the derivative, and we got the term where we are taking the derivative of u and v, so those term we have equated to 0. So that is one condition. And next what we did is we just took the another derivative and then substituted back into the original equation, and then we combine the equation, like combine the terms which corresponds to the first complementary solution, and then this is the second complementary which is like y2. So after doing that, we got this the form which has been much reduced form that we have got, and this is the imposed condition that we have imposed. So after solving this, we'll get u and v, and the particular solution will be u y1 plus v y2. So that's all we have done. And then u is equal to minus of y2 f of x dx, and that is Wronskian element, and then v is equal to integral y1 f of x dx and Wronskian. Okay, so this is like this one was like might be tedious, but then once you do it once yourself, it will be clear. Okay, so this one was the one of the way to find the particular solution. So we'll take one example for this, and then we'll see how we can get the answer. Okay, so I will solve one problem which is d square plus 4 y is equal to sec of 2x. Okay, so you can see that this is not the some regular term which is like might be complicated to solve if we go directly. So we'll see how to solve it. So first of all, what we'll do is we'll find the roots for this, which will be d is equal to plus minus 2y. Okay, so y complementary will be c1 e raised to 2y plus c2 e raised to minus 2y, and we can separate out and then write everything in cos and sine, and what we will get finally is a, let's say a cos, a cos of 2x plus b sine of 2x. Okay, so this is a complementary solution that we have. So what we'll now move is we'll move to particular solution, and instead of a and b, what we'll write is u cos 2x and v sine of 2x. Okay, so u and v are the functions of x, and now what we'll do is we will use the derivation that we did before. So u is nothing but minus y2. So you can see this one, y1 is nothing but cos 2x, and y2 is sin 2x. So we'll substitute y2 is y2. Okay, I will write first f of x dx and y2 and y1 prime y2 prime. Okay, so minus y2 is sin 2x, f of x is sec of 2x, and dx, and we'll determine this here first because it is common to both. So y1 y2 y1 prime y2 prime. Okay, so y1 is cos 2x, y2 is sin 2x, y1 prime is minus 2 sin 2x, and y2 prime is cos 2x, and 2 will be there. Okay, so if we find the determinant, which will be 2 cos square 2x plus 2 sin square 2x, which will be 2. Okay, so that is good. So if we put it here, so what we will get, u is equal to minus integral of, so we'll take this half out, and then sin 2x by cos 2x. So sec of 2x is 1 upon cos 2x, so half we'll get tan of 2x dx. Okay, so the integral of tan x will be log of sec 2x, and we'll take this minus sign out inside, so it will be log of cos of 2x. Okay, so we got u. Yeah, that is good. So we'll find out v now. So the equation that we'll use is this one. So v is equal to y1 f of x dx, f of x dx, and Wronskian. Okay, so Wronskian was 2, so we'll use directly. So y1 is cos 2x, cos 2x. F of x is sec 2x dx. Okay, so now cos and sec will get cancelled, and that will be 1. So integral of 1 by 2 dx will be x by 2. Okay, so y particular we will write now u into cos 2x plus v into sin 2x, which is nothing but u we have, so half of natural log cos 2x plus x sine of 2x by 2. Okay, so this is a particular solution that we got. So the total or the general solution will be yc plus yp. So we'll just write out. So this is the complementary a cos 2x, plus b sin 2x, and we'll write now particular solution which we just determined. Half of so we'll take this cos first, so cos 2x by 2 and log of cos 2x, okay, plus x by 2 sin 2x. Okay, I hope this the procedure is clear, how to use the Wronskian and how it came. Okay, you can practice also. Yeah, that's all I have today. Any doubts in this? Okay, if there are no doubts, we'll stop the session.